now we go from Moscow, Russia to Chile. And the next speaker is Karin Alfaro-Bittner. And she will present us results on growing scale-free simplices. So if you're ready, Karin, you can share your screen and the floor is yours.
Thank you very much. So thank you to the organizers for inviting me. And in this talk, I will talk about growing scale-free simplices. So it's not new that that most of the real networks are have this scale-free property, but also most of the cases that we can describe by a network are not well described by a pairwise interaction. So here you have some examples of them: scientific collaboration, social interaction, even competition for food. You have that not only two components or unit components of the network interact, so it's beyond of that. So here we talk about that it's necessary to include high order interactions. There are many cases of this, even including brain networks. So one of the candidates to avoid to answer or trying to describe this high order interaction are simplicial complexes. So a zero simplex is a node, one simplex is a link, two simplex a triangle, and then you have 3, 4, and etc. So given the data set, this kind of description has been during this last years has been very, very important to include this kind of interaction. So can we grow a network considering a high order interaction and controlling its statistical properties? And the answer is yes, it has been already done. So let me explain how this growing processes is. So we can start from a click with this transitivity coefficient equal to 1. And the condition is that each link is part of a triangle, but also, okay, the initial seed is much smaller than the total number of nodes that we will include, we will add to this network. So this has been already done in the, you can see this these articles. So for T=1, we want to add this node by the restriction that must to form a new triangle. So let me introduce some notation that we will use during this presentation. And let's call M _3 the number of new triangles. Then the number of new nodes, it will be exactly the same quantity. And for the case of the number of new links, we have this is the double of the M. So for M = 1, we have the cases that this case that we have one node and two links. All most of the description that I will do is introducing just using m equal to 1. But okay, this process can be done by using 3 ways to grow this network. The first one is the non-preferential case. The second one is the preferential, that these both cases are already reported. And the second one, that is the new one that we are proposing, is the mixed case. So in the non-preferential case, we have that the probability that a node A, sorry, I put A selects the link ij at time t. So in this case, we have that these terms are due to the initial number of links, and the other one is the new links at time t, the t minus 1. Yes, because we are considering the configuration of the configuration for t depends on the configuration in t minus 1. So all the links in this case have the same probability to be selected by this node A, sorry. And in the case of the preferential case, we have that this probability, it's due to, okay, we have this generalized degree of the link, of this link at this time. And this term is describing the number of triangles formed by this link. And of course, in this case, the probability is proportional to the degree, the generalized degree. So in this case, when we consider the evolution of the number of nodes with certain degree, k, at time t, for the non-preferential case, we have this differential equation that considers the degree of the one time before t, time minus 1, and with this term, and also is considering all the new links that we are nodes, sorry, that we are including. If we look for certain kind of solution, and considering that if we add more nodes, I mean, not just 1, 3, or 4, or whatever, the number of nodes at time t is scaled as t. So we look for this kind of solution, and then after some calculations, we can find the degree distribution as this expression. But the most important is that it goes like a power law. Also, we can do similarly to what is explained before, and we can find the distribution of the generalized degree for the non-preferential case And we find this expression that is this exponential. We can do, I would not say exactly the same because it's not so easy for the preferential case, but we can find some this expression for the degree distribution and also for the generalized degree in the case of preferential case, and both of them are a power law. So here we can find some figures that shows that our theoretical approach it's quite good for the description of these growing processes. And okay, for in this case, remember that it's exponential, and okay, in most of the cases, the agreement is quite good. So let us see a schematic visualization of the network, and here we have this one for the non-preferential case and the preferential one, and we can see we can distinguish some difference. The first of them is that the value of the link degree for the non-preferential case is this interval, the values that I can that are allowed for this are smaller than for the other case, and also we can see that in this case we can see that this visualization, or this in this case the network is more heterogeneous. I mean, we can observe links with degree 1, 2, and even with 6. Also, compare with this one that we can observe just a few of them. And in this case, this visualization was considered that the lines, the width of these lines are proportional to the link degree, but and also the size of these nodes, it's proportional to the eigenvector centrality. So, okay. So let us now consider the mixed model. I mean, a model that includes the non-preferential, preferential, and the preferential case. And in this case, we consider this term as the number of links, and this is the generalized degree at time t of the link. And of course, if we with A and B being constant, but in the case of A being 0 and B equal 2/3, we recover the preferential case, and in case of A equal 1/2 and B equals 0, we recover the other case. So if we consider that the sum of the all probabilities should be equal to 1, we have an expression to link these both quantities, I mean these both constants. And considering that this probability should be non-negative, then we find the intervals for some intervals for A and B. So here you can see that, well, after calculations, you can find that this distribution of the degree and on the link degree, it follows a power law. So this is the exponent gamma, and by tuning B, we can of course have a different value of gamma, and the same for the generalized degree. And as you can see, this is for you can see that we can tune all the statistical cases that we want. And the approach, of course, this approximation is quite good. So, okay. Even the same growing process can be done for the uniform hypergraph. So considering that D is the dimension, for example, for D equal 2, we form a triangle, and for D equal 3, a square, and a pentagon for D equal 4. So if we add exactly as before, not completely exactly, but we introduce, for example, a node. In the case D equal to 2 nodes, D equal 3, sorry, and D equal 4, 3 nodes. We are adding, well, 2 hyperlinks, 3 hyperlinks, and 4 hyperlinks. For this growing process, of course, we can have a expression for the probability that a specific link is chosen by this hyperedge. And in this case, with the non-preferential and preferential case, with the same, using the same constant, we have these results where you can see that it's also following a power law, but in the case of in most of the cases, we can say that it's following a power law, but in the case of non-preferential case, that is this solid curve, remember that it wasn't a power law for the previous case. So just summarizing, we have we extend this growing process for the initial one that it was for non-preferential and preferential. Is known as network geometry with favor, and we introduced this mixing model when we can tune by tuning this constant B, we can change this the exponent of the power law, and then we can control the structure of the network that we want to construct. And also we made an extension for uniform hypergraph, and it's following exactly the same behavior as before. So thank you for your attention.
Thank you a lot, Karin, for your beautiful presentation. I see Jose is back with us. So at the end of Karin's presentation, I will leave Jose the leading of the event. So is there any question for Karin from the audience side?
Yeah, I have one question, Karin.
From India to Chile, Pitamba.
Yeah, yeah. So actually, at first you have started with a 4-node complete graph, right? To add one node one by one, and it will grow to a Scalefree network. In the third or fourth slide, you show that one 4-node complete graph, right? And you have started adding node one by one.
Yeah.
Yeah. In this slide.
Mm-hmm.
So if we take in a random network initially, then also it will grow to a Scalefree network.
Sorry, if you take what?
One random network initially, instead of this 4-node complete graph.
Instead of a click, you need a seed. I don't think this changed because the seed, the initial seed is very little. So the structure of the degree distribution is made by the sequence of added node. So you take a seed at the beginning for convenience, because you don't have to generate a seed. You just take a complete graph at the beginning.
Yeah.
Okay, and one more question: is there any rule for critical time step? That means, suppose after 1,000 time step, we will reach to a Scalefree network. Is there any rule like that, or we have to check in every step?
Okay, in this case, we consider the networks that we took was it was let me see, it was 10,000 nodes. So yeah. I think that
I think if it helps the k-cut, so the maximum degree it should go like t power 1/2. So if you want a large degree to have a good statistics, you have to have a big time, you know.
Now, Jose Mendes is very expert of this, because you have to know that when after studying the Barabasi-Albert model, I immediately studied also the growing model Dolgoronchev and Mendes, which is the number 2 in the list. So.
Okay.
Okay, so are there any other questions from the group, from the group, from the audience? Okay, if not, I thank you again, Karin, for the beautiful presentation.